Hello guys, I am Tanish Sharma, student of International Institute of Professional Studies, and my roll number is IT2K1963. I am going to solve the first internal of analysis and design of algorithm. So, now we are going to know about the time complexity and the space complexity. So, the time complexity of an algorithm quantifies the amount of the time taken by the algorithm to run as the function of the length of the input. Next, the space complexity. The space complexity of the algorithm or a computer program is the amount of memory space required to solve an instance of the computational problem as a function of characteristics of the input. So, now we are going about the table. The first is linear search. Now we are find the time complexity and space complexity, the power complexity of the linear search with the relation. Linear. The recurrence relation for the linear search algorithm is step 1. Define the recurrence relation. I would define the recurrence relation for the time complexity of linear search, which we can derive from the worst case scenario. The recurrence relation would be T of n, the T of n minus 1 plus 1 if the target value is not found in the first n minus 1 elements. The T of n equal 1 if the target value is found in the first element. T of n is equal T of n minus 1 plus Vigo of C, where n is the size of the input and C is the constant time taken to compare an element list with the target element. Step 3. Solve the recurrence relation. After defining the reference relation, I would explain how to solve it is using mathematical induction. I would start with the base case, the t of 1 is equal 1, and then assume that t of k is less than equal k for all k is less than n. I would then show how is this assumption leads to inequality t of n is less than equal n using the two case defined in the recursion relation. Therefore, the time complexity of the linear search algorithm is big of n. This is because in the worst case of the algorithm needs to compare every element in the list with the target element. To solve this recurrence relation, we can use the recursive 3 method. The recurrence relation can be written as the step of the t of n is equal t of n minus 1 plus c, the t of n minus 2 plus c, the t of n minus 3 plus c plus c plus c, and the t of 1 the plus c plus c plus c and the plus c, the n minus 1 times the Vigo of n. The space complexity of the linear search algorithm is the Vigo of 1 because it is, does not require any additional space beyond the input list and few constant variable used for indexing the comparison. The power complexity of the linear search is Vigo of n, which means that the running time is algorithm growly linear with the size of input data. In the words, in the input is the last doubled, the running time is algorithm will also double. The power complexity is expressed as the exponential in the big zero notation, which represent an upper bound the growth rate of the running time as the function of the input size. The power complexity of linear search is relatively simple and easy to understand, but it may not be the efficient algorithm for the large dataset or complex search conditions. Now, we are going to know the time complexity, space complexity, and power complexity of the binary search with this relation. So, step 1, we want to find the position of the target value 7 in the list using binary search. The step 2, define the recurrence relation. The recurrence relation for the worst case scenario of binary search is the T of n, the T of n divided by 2 plus 1 if the target value is not found in the middle element. The T of n is equal 1 if the target value is found in the middle element, where n is the size of the search space. Step 3, explain the intuition behind the recurrence relation. In each iteration of binary search, we divide the search space in half, and therefore the size of the search space decreases by the factor of 2. This leads to the recurrence relation where we divide the problem size by 2 at each step. Step 4. Solve the recurrence relation, a recurrence tree with the root node representing the entire list of n elements and each child node representing one of the two sublists obtained by dividing the search space in half. I calculate the number of comparisons mode at each level of the tree, which is 1 for the root node, 2 for each its children, 4 for each their children, and so on until we reach a leaf node representing a sublist of one element. I would then sum up of the number comparisons made at each level to obtain the total number of comparison made by the binary search, which is T of n is equal n log n plus 1. In the worst case scenario, I would explain how this solution gives us the time complexity of binary search, which is Vigo of log n. To solve the recurrence relation, we can use the recursion tree method. The tree of this example look like this. Yeah, would you show like the on screen? Starting from the root node, we check the middle element, which is 8. Since 7 is less than 8, we move to the left subtree, which has the size of 5. We then check the middle element of this subtree, which is 4. Since 7 is the greater than 4, we move the right subtree, which has the size of 2. We then the check middle element of the subtree, which is 5. Since 7 is less than 5, we move on the left subtree, which has the size of 1. We then check off the middle element of the subtree, which is 7. We have found the target value. So the number of comparison made is 3. The power of complexity of a binary search is Vigo of log n, which means that the running time of the algorithm grows logarithmically with the size of the input data. In other words, if the input tree. Starting from the root node, we can check the middle element, which is 8. The power of complexity of the binary is Vigo of log n, which means the running time the algorithm grows logically with the size of the input data. In other words, if the input size is doubled, the running time is algorithm will increase by the constant factor. Example, one additional comparison of average. The power complexity of the binary search is much better than that of the linear search for large data sets, as it enables the algorithm to quickly narrow down the search range by discarding half of the remaining items at each step. This makes binary search a highly efficient algorithm for searching sorted arrays and other ordered data structures. Now we are find the time complexity and space complexity and power complexity of the factorial. So the T of n is equal T of n minus 1 plus the Vigo of c, where n is the input to the factorial function and c is the constant time taken to perform the multiplication operation. To solve this recurrence relation, we can use the recursive tree method. The recurrence relation can be written as T of n is equal T of n minus 1 plus c, the T of n minus 2 plus c plus c, the t of n minus 3 plus c plus c plus c, the t of 1 plus c plus c, and the n minus 1 times the Vigo of n. Therefore, the time complexity of the factorial function is Vigo of n. This is because the function calls itself recursively n times and performs the multiplication operation in each call. To compute the factorial of 4, we need to multiply n with the factorial of n minus 1. We can continue this process until we reach the best case of not equal 0, which is defined as 1. In each iteration of the recursion, we reduce the size of the problem by 1 until we reach the base case of 0. This leads to the recursion relation where the subtract 1 from the input size at each step. To solve the recurrence relation, we can use the recursion tree method. The tree of the computing the factorial of 4 looks like this. Starting from the root node, we compute the factorial of 4 by multiplying it with the factorial of 3. We then compute the factorial of 3 multiplying it with the factorial of 2 and so on until we reach the base case of not equal 0. The total number of operations performed is 5. Using the recurrence relation, we can also derive the closed form expression for the time complexity. The T of n is equal to T of n minus 1 plus 1, equal the T of n minus 2 plus 2, the T of n minus 3 plus 3. So, the T of 0 plus n and n plus 1. Therefore, the time complexity of computing the factorial of n using recursion is 0 of n, where n is the input size. The space complexity of the factorial function is 0 of n because the function call itself recursively n times and each call creates a new stack frame on the call stack. The call stack therefore has maximum depth of n, which is the space required by the function.
Now we are discuss about the Tower of Hanoi to find the space complexity and the time complexity and power complexity. The T of n is equal to T of n minus 1 plus we go of C, where n is the number of disks to be moved and C is the constant time taken to perform a disk move. To solve the Tower of Hanoi problem for n disk, we can break it down into smaller sub-problems. Specifically, we can solve the problem for n-1 disk by moving the top n-1 disk from the starting page to the auxiliary peg and then move the largest disk from the starting peg to the destination peg. Finally, we can move the n-1 disk from the auxiliary peg to the destination peg. This requires 2t of n-1 plus 1 moves. To solve this recurrence relation, we can use the recursive tree method. The recurrence relation can be written as t of n to t of n-1 plus c, 2 of 2t of n minus 2 plus c plus c, 2 power 2t, and this is the steps all you can see. To solve for t of 3, we can use the recurrence relation t of n is equal to t n minus 1 plus 1, which tells us that the number of moves required to solve the Tower of Hanoi problems with n disk is twice the number of moves required to solve the problem with n-1 disk, plus one more move to move the largest disk from page A to page C. Using this formula, we can express T of 3 is terms of T of 2. The T of 3 is equal to T of 2 plus 1. To find T of 2, we can use the same formula with T of 1. T of 2 is equal to T of 1 plus 1. And to find T of 1, we can use the formula T of 0. T of 1 is equal to T of 0 plus 1. We know that T of 0 is the base case, which is simply 0 moves required to solve the problem with no disk. So we can start the evaluating T of 1 using the formula. T of 1 is equal to T of 0 plus 1 is equal 2 of 0 plus 1 is equal 1. This tells us that it takes one move to solve the problem. Which one disk next? We can use the result to find T of 2. T of 2 is equal to T of 1 plus 1. 2T of 1 plus 1 is equal 3. This tells us the it takes 3 moves to solve the problem with 2 disks. Finally, we can use this result to find t of 3. The t of 3 is equal to t of 2 plus 1. 2 of 3 plus 1 is equal 7. This tells us that it taken 7 moves to solve the problem with 3 disks. So, the solution of the recurrence relation t of n is equal to t of n minus 1 plus 1 for n is equal 3 is t of 3 is equal 7. Therefore, the time complexity of the tower of Hanoi problem is we go of n power 2 power n. This is because in the worst case, the algorithm needs to make 2 power n minus 1 disk moves to complete the problem. The space complexity of the tower of Ni problem is we go of n because the function call itself recursively n times and each calls creates a new state frame on the call stack. The call stack therefore has a maximum depth of n, which is the space required by the function. Now we are knowing the other time, power, and space complexity. The binary tree traversal. The time complexity is V go of n, and the space complexity is V go of n, and the power complexity is V go of n. The merge sort. The time complexity V go of n log n. The time space complexity V go of n. The power complexity the V go of n log n. Quick sort best. The time complexity of quick sort best we go of n log n, the space complexity we go of log n, and the power complexity we go of n log n. Quick sort at worst, the time complexity we go of n power 2, space complexity we go of log n, the power complexity we go of n power 2. Iterations matrix time complexity we go of n power log 7, the space complexity we go of n power 2, the power complexity we go of n power log 7. Karatsuba integer, the time complexity we go of n power log 3, the space complexity we go of n power log 3, the power complexity we go of n power log 3.
Now, the second question is write recursive algorithm for polynomial representation. So, this algorithm defines a class polynomial with a constructor that takes a list of coefficients. The evaluate method the evaluates the polynomial for a given value of x. The base case of the recursion is when the polynomial has degree 0. Example, it is the constant polynomial. In this case, the method simply returns the single coefficient. In the recursive case, the method creates a new polynomial p of degree n minus 1 by removing the highest degree coefficient from the list of coefficients. It then recursively evaluates p for the given value of x and multiples the result by x. Finally, it adds the highest degree coefficient to obtain the value of the polynomial for the given value of x. The algorithm works by breaking down the problems of evaluating the polynomial of degree n into the problem of evaluating a polynomial of degree n minus 1. It uses the fact that the polynomial of degree n can be expressed as p of x is equal q of x plus c, where q of x is a polynomial of degree n minus 1 and c is the highest degree coefficient. This allows the evaluation to be performed recursively by computing q of x and multiplying by x and then adding the highest degree coefficient. Start with the original polynomial of the degree n and a is given of x. Check if the polynomial is constant. Example, it has only one coefficient. If yes, return the coefficient as the evaluate result. If the polynomial is not constant, compute the polynomial of degree n minus 1 by removing the coefficient of the highest degree term. Recursively evaluate the polynomial of degree n minus 1 for the same value of x. Multiply the evaluated result of the polynomial of degree n minus 1 by x. Add the coefficient of the highest degree term to the result obtained in step 5. Return the final result as the evaluated value of the original polynomial for the given value of x. Class polynomial defined in itself, and in this would show to a screen the algorithm. Uh, the last result is equal result into x plus self coefficient minus 1 the result return. The third question is write iterative version of Tower of Hanoi problem. Initialize the stack with the initial state of the problem. Example, all of the disk on the first peg with the larger disk on the bottom and the smaller disk on the top. While the stack is not empty, do the following. A. Pop the top state of the stack. B. If the state represents a solved problem, example, A1 of the disk are on the third peg in the correct order, then return the state. C. Otherwise, find the top disk on the peg that is the currently on. D. If the top disk can be moved to another peg without violating the rule of the problem. Example, a larger disk cannot be placed on the top of smaller disk, then move the top disk to the appropriate peg and push the new state of the problem onto the stack. E. Repeat step BD until the problem is solved. If the stack is empty and the problem has not been solved, then the problem is unsolvable. This implementation uses a stack to keep track of the recursive call that would be made in the recursive version. The stack starts with the initial call to move n disk from road to the to road using the aux road as a intermediary. In each iteration of the loop, the top call is popped from the stack and executed. If there is only one disk to move, it is moved and the loop continue. Otherwise, two recursive calls are pushed onto stack. One to move n minus one disk from road to aux road using the to road as intermediary, and another to move n minus one disk from the aux road to road using from road as intermediary. Finally, the call to move the remaining disk from row to row is also pushed on the stack. This process continues until the stack is empty, at which point all the necessary moves has been made to solve the Tower of Hanoi problem. This is all the step of the Tower of Hanoi iterative version you can see. Thank you.